The third kind of energy we're going to talk about, we talked about kinetic, we talked about gravitational. Our third kind of energy is we got to talk about heat energy. I said it a couple times. It took physics people a long time to figure this out. This is the one that really hurt people's heads. Um, Heat is actually a form of energy. On the one hand, that should kind of make sense to us. It takes energy. Things just don't naturally get hotter. You've got to do work. You've got to spend some energy to heat things up. But where it gets weird is then the flip-flop of it. If things are hot, they have more energy. We should be able to, energy means the ability to do work. So if you had something hot, it takes some clever engineering, but in theory, something hot should be able to do work on something else. Like something like a bowling ball with kinetic energy could do work on something else. If you had something hot it would take some engineering, but something hot has more energy than something cold. It should be able to push and make something move around. That's what took people a long time to figure out. Way back when they didn't understand it, they thought heat was a fluid and they called the fluid caloric. That's why we have calories still kind of kicking around. And they thought, like a candle, when you burned a candle, it got smaller because it was losing its heat fluid. They just didn't get it. So it took a bit of time. That Joule guy that I mentioned, this is kind of where he shone, messing around in his parents' brewery. He used pulleys and weights and he stirred water like crazy and showed that the kinetic energy that they put into stirring the water actually increased the temperature. So that's kind of, it took a while to get here, but this is where we are now. Um, Basically, common sense, you can't just have things warm up without putting energy into them. It takes heat energy to get something to go from one temperature to a warmer temperature. Um, Building our equation, the heat energy it takes. And again, kind of common sense. Like imagine you had to heat something up. What would take more energy to heat up? Well, one thing that's going to matter is it depends on how much stuff you're heating up. If I'm heating up a cup of coffee compared to a big pot of water to make soup, or compared to a hot tub to go sit and warm up after shoveling snow, it's going to take more energy to heat up more water, let's say. So the mass of the water, the mass of the thing that we're heating, kind of affects how much heat energy it takes to heat something up. The second thing that affects heat energy is what the heck are you heating? Um, Often we'll talk in physics about heating water because we've got so much water on Earth. Water is special. It takes a lot of energy to heat up water. That's good for us on Earth because that means that the temperatures on Earth don't swing too crazy hot and too crazy cold because water's got this almost like inertia that's hard to heat up. We don't get crazy hot. We don't get crazy cold. Geography people call it a moderating effect. In physics, the fancy term for this idea of how much it takes to heat something, whether it's water or a metal or something else, they call it the heat capacity, or sometimes they call it specific heat capacity. Heat capacities are going to change from material to material. Water's got a very high heat capacity. Metals tend to have a lower heat capacity. And the third thing that depends on that heat energy depends on is like how much are you heating it? Are you heating it up a couple of degrees or are you heating it up to boiling? Oops, change in temperature. That's the word equation for heat energy. The math equation, we've seen mass a bunch of times. The short form for mass is lowercase m. Heat capacity, or sometimes called specific heat capacity, it's capital C for capacity. And change in temperature, the short form for change in is the delta, and temperature we're going to go capital T. Now, if physics people were in charge of this, if physics people had control, heat energy should be capital E with a little h. Like kinetic energy was E with K, gravity energy was E with G, friction energy was E with F or E with the word friction. So you would think heat energy would be E with a little h. I'm going to blame chemistry people. They got involved, and chemistry people called this capital Q. So you may have seen heat energies in chemistry class, capital Q. Sometimes people nickname this the Q equals MCAT equation. When we start rolling with it and practicing it, it's MC T2 minus T1 in brackets. This equation tells us how many joules of energy it would take to heat something from one temperature to another. If you're heating a lot of stuff, a lot of kilograms, it's going to take a lot of joules. If you're heating it from cold to hot, like a big temperature swing, that's going to take a lot of joules as well. In a way, it's just a plug and chug. Here, let's practice one. Appropriate for me, I'm a coffee, I don't know. I was going to say snob, but more is I drink too much of it. Let's say we want to heat up some water to make a coffee. This capital C thing with the funny units, that's the specific heat capacity. Basically, this number, 4,186, tells you how many joules it takes, how much energy, to heat 1 kilogram by 1 degree Celsius. If you had exactly 1 kilogram and you wanted to heat it up by 1 degree Celsius, it would take 4,186 joules of energy. If you're using a battery pack, the battery pack would go down by 4,186 joules to heat up 1 kilogram by 1 degree Celsius. Our equation, this one back here, it'll be typed and given on our equation sheet. Q equals mc delta T. Just a number crunching thing. Oh, we got to go in kilograms. It's been a while, but to go to kilograms, 3 decimal places, so 0.450 kilograms. A little bit lazy, so I'm just going to call it 0.45, not put that last zero. 4186 is the heat capacity. I've seen some textbooks round that off, so if you're looking online, you may see it called 4,200 instead of 4186. Just a difference, just a academic really. And then change in temperature is always the second temperature minus the first temperature. Change in anything is always second minus first. So for this one, it's going to be 85 take away 25. So 0.45, 0.45 multiplied by 4186, and then 85 minus 25 is 60. Grab your calculators, make sure I don't goof this up. But when I do this, I get a big number, 113,022 joules. Because water's got a big heat capacity, it takes a lot of energy to heat up even just a little bit of water. That's why like your stove takes that big plug, or a natural gas stove, your water heater in the basement of your house or your rental. Hopefully it's natural gas because it's a little bit more efficient at heating natural gas than electricity. It just takes a lot of energy to heat water. That's why if you live near a lake, it's a little bit cool in the spring as the water in the lake takes time to warm up, and a little bit warm in the fall as it takes time for the water to cool off. If we wanted to be better with scientific notation, this one should probably only have 2 digits. So 1.1 times 10 to the 5 when we're in joules. All right, practicing another one. Let's switch away from water. Let's say a blacksmith, a welder, just somebody working with metal, heats up a bunch of metal. This time I gave you the Q value, the 945 in joules, that's the Q. So 9.45 times 10 to the 4 equals the mass I made up was 1.2. That's a hefty piece of metal. We don't know the heat capacity, so that's going to be our unknown. So I'm going to leave that as capital C. Change in temperature is always second minus first. So 120 take away 15. I'm pretty messy at writing brackets. So I'm going to deal with those brackets right off the bat so I don't forget what they are. 945 times 10 to the 4 equals 1.2 times C. 120 minus 115 is 105. Now we got some calculator work to do. We're nearing the end. Hopefully you're still buying in. To make sure you're buying in, I'm going to skip a couple steps, get your calculators out and practice it. When I did it, I got 750, nice and clean. The units on heat capacity, it's how much energy to heat up 1 kilogram by 1 degree Celsius. So its units are joules per kilogram degree Celsius. We're going to pause there and then we're going to wrap it up.